Okay, we're going to look at section 6 now, which is cell EMF under non-standard conditions. So we're not looking at 298 degrees Kelvin, and we're not talking about what it would be compared to just the SHE. Okay, it's going to be something different. You're going to be not at equilibrium. You're going to be with a different number of products, different number of reactants, that kind of stuff. So as the voltaic cell is discharged, your concentration actually changes until your E equals 0. Okay, until that overall E equals 0. Now this E naught here, okay, E naught is still your cell potential. Okay, that's not going to change. All right, but what might change is if I have more products or reactants, okay, the actual E for the entire cell or the entire reaction will change. So this this equation is on your equation sheet. Okay, actually both of them are. The top one is E equals E naught minus RT over NF. And that's that fancy F, the Faraday's constant. R is still the 8.314. T is your temperature. And N is still my number of electrons. And it's a natural log of Q. Q is your reaction quotient, which is the products over your reactants. Okay. If you want to do this at 298 Kelvin, okay, that's now when we look at, we have R is a constant, T is going to be 298, and F is a constant. So we can take all three of those numbers and actually do the multiplication and division, and we'll get out 0.0592, that blue number there. Okay, so at 0.0592 over N times the log of Q. And that blue equation is also on your equation sheet. So if it's at 298 Kelvin, you can just use the bottom one, which it usually is. If it's not at 298, you're going to have to use the top one, but way more likely to be at 298. Okay, now if we talk about these cells in our cell EMF, okay, as my reaction starts to go, my number of reactants is going to go down. Well, as your number of reactants go down, my product over a reactant, that number starts to get larger. Well, as this starts to get larger and larger, this whole part here on the right side of my subtraction, okay, gets larger and larger. Well, what happens is this is a set number. Say it's 4.3 volts, okay? I'm going to start subtracting a bigger and bigger and bigger number from 4.3 until eventually it's the same and my cell stops. Okay, so that's what happens as my cell gets what we call discharged. All right. If your reactant number goes up, okay, I add more of my reactants in there. Okay, your EMF is starts going to go up and actually drive the reaction forward because I have more and more and more of these reactants. I'm going to have more and more electrons that are starting to move. Okay, so again, it's just a non-standard condition where you're dealing with how many products or how many reactants you have. So if they're giving you concentrations of both, you're going to need to use them. Okay. So in this next practice problem, we're going to calculate the cell EMF at 298 Kelvin by a cell that was described in an earlier practice problem. It was in sections 3 and 4. I have some concentrations there, and I have my reaction. I've kind of already done this one, so you'll see that I have my reaction there at the very bottom. All right. All I want is my E. Okay, overall. Well, if I want my E overall, that means we're going to be using this blue equation where you have the E naught, which is just the cathode minus my anode. And all I got to do now is plug in all of these concentrations. And that is really, literally all you are doing. My E naught is 0.79. That's probably, you might think it would be the harder part to do. Okay, you have to go through and figure out what's your cathode, what's your anode. But since we already did this in 3 and 4, you don't have to do that. You already know that your cell EMF or standard EMF for that one is actually 0.79. I gotta know that my N is 6. How do I know that N is 6? Because it's 6 negative here. I have 6 negative iodines. So I have 6 electrons that are being transferred because it goes from 6 negative to 0. So all 6 of those electrons got moved. Right? And then you do a little bit of math. Overall, your cell voltage is 0.89 volts. Okay, the last thing we're going to look at in 6 is what we call a concentration cell. Okay? Concentration cells can be kind of tricky. So let's just look at this top part here, all right? Cell EMF depends on concentration. So a cell can be made by using the same species at a different concentration. Okay? These are called non-standard conditions again, and they go until your concentrations are actually equal. Well, what we've got going on in this top little beakers are we have a nickel anode and a nickel cathode, but one beaker has a much smaller molarity than the other. The one on the left has a very small molarity. The one on the right has a molarity of 1. So I got to figure out which one's going to be my cathode, which one's going to be my anode. Okay. under a standard condition, okay, it's going to be 0 because I have nickel one way and nickel the other way. One has the anode, one has the cathode, so it would be 0. But these are non-standard conditions again, so it's going to go until your concentrations are actually equal, okay? So at my anode, we've got that top going on, okay? I have nickel going to nickel 2+, plus 2 electrons, which would make sense. My cathode, I have nickel 2+ going to nickel because it's being reduced, okay? So now the question is, how do we know which numbers we're going to put where, okay? I know, okay, that your anode has to be the one, like it says up here, which would be my smaller concentration, okay? Because my anode is going to make a higher concentration of solution, a higher concentration in my solution, because we're going to be producing more of these nickel ions, okay, at an anode, all right? We're making more of these Ni2+, putting them into my solution so my electrons can move around. So you're going to make more of this concentration or more of this nickel ion and become higher, so that has to be my anode. I knew the lower or the higher concentration has to be the cathode because that's the one where you're going to have less of my nickel 2+ in there. Okay, so I'm going to try and make them equal. So this one's going to make more and more and more nickel ions to try and catch up to the one on the right who's going to be using up more and more and more nickel ions. So we'll start out with not very many on the left and a whole bunch on the right, and then eventually they should equal. Okay, so when I take my E equal to my E naught is 0 in standard conditions. I got nickel one way, nickel the other. Okay, that number is going to be the exact same. That's 0 minus 0.0592 over 2 because I have 2 electrons going places. Okay, times the log of products over reactants. Well, my product is the 1 times 10 to the negative third because it's a smaller concentration. And my reactant is the larger concentration because that's going to be the one on the left. So you basically got 2 nickel. You basically have 2 nickel concentrations. That's actually how pH meters work. pH meters work by membrane concentration differences, and these ions move back and forth over your membrane. Go ahead and try the last one, and here is your answer.